Good morning, everybody. Today I'm going to talk about a project I have with people in Oxford, Tessa Baker, Pedro Ferreira, Macarena Lagos, and Johannes Nuller. And it will be about effective field theory, effective field theories, in particular how to construct general effective field theories with different ingredients. And if it is possible, I will ask myself if it is possible to get a unified description of all these effective theories. But before going on, it's better to have clearer in mind what do I mean by effective field theories at plural. So suppose we have generic actions, even fully covariant, describing gravity with a metric g mu nu coupled to either a scalar phi or a vector, a mu, or a tensor. Suppose also that these actions share some properties. They all have one scalar propagating degree of freedom. They are invariant under linear diffeomorphisms. They have maximum two derivatives in the action. And through scalar vector tensor decomposition, they are quadratic in perturbation. So we want linearized actions. So if all of these three kind of actions share the same properties, can be unified, which means, is it possible to write down a single action describing the linear phenomenology of all of them at once? So you're expecting yes as an answer, but I don't think so, and I think it's not possible. But this is not the end of the story, and I would like to describe you still the method you can use to construct these actions and why it's not possible or why it is difficult. So first, let me review something that should already be known, which is scalar-tensor theories. It's well known. What's the answer for having an action linearized with these properties? And basically, the effective field theory of dark energy gives us the action. We already have it. It's in the literature. It's nice. If we restrict up to second order in derivatives, we have linearized Ordensky. The effective field theory in general has infinite operators, but if you want just two derivatives, you can get you have fewer operators, and they are finite. They are 5 in total. The first of them is something that parameterizes the expansion history of the universe as the Abel rate. The other 4 are present just in at the perturbation level. We name them one kineticity, one braiding, one Planck mass run rate, and the last one tensor speed excess. The kineticity is basically the standard kinetic term of quintessence models. If you want, the braiding is a mixing between the kinetic term of the scalar and the metric. The Planck mass run rate is the time derivative of an effective Planck mass, defined as the normalization of tensor modes, and the tensor speed excess is something that determines the speed of gravitational waves. This is something that it is known. You can express it in a different basis, in their original basis. But suppose we want to construct something different. We want to construct something with a vector and a tensor. There is literature, of course, but what I'm going to show you a generic method now, with which you can construct generic effective field theories specifying few things. And the recipe is this. I'm giving you first the recipe and then an example. You choose the field present in a theory and the gauge symmetries to be satisfied. You write down an action with all possible quadratic interactions between the fields, leading to a given maximum number of derivatives of the fields in the equation of motions, and at the end you find the nature identities associated to the required gauge symmetries and impose the resulting constraints on the quadratic actions. So summarizing, basically you have to choose just fields, gauge symmetries, number of derivatives, and the rest is done by your PC. your computer. I mentioned the computer because as you'll see, it's a quite expensive method to do it by hand. It's not impossible, but I like it. I particularly like it because it's very simple and with a bit of Mathematica or so, you can write down something really generic without much effort. So suppose I want to work with vector tensor theories. My fields will be the metric, a vector field, plus matter. Matter, I will consider matter just a minimally coupled scalar field. Then I want the full action to be invariant under linear diffs, and I want maximum two derivatives a la Ordensky, say. The first thing I have to do, since I mentioned first scalar vector tensor decomposition, I have to decompose my ingredients into a background and a perturbations. I have here the usual decomposition of the metric with 0, 0 components, 0 I, ij. Each of them can be decomposed into 4 scalars, psi, b, phi, and e, 2 vectors, s and f, which are divergenceless, and a tensor, which is traceless and divergenceless. In the same way, I can decompose the vector field with a background a bar plus the zero perturbations and a spatial perturbation. And in the same way, the matter field. Now, I want here just to show you how to follow the recipe. You write down a generic action with the ingredients already split in space and time. Here, the Lagrangian is a function of generically the metric and the vector field, plus you have the matter. After that, you need something to calculate all the possible scalars you can get from this action, containing at most 2 derivatives. Here there are some examples, but the ellipsis here means that you can go on forever. There are a lot of terms, okay? But still, this Lagrangian is implicit. Then what you have to do is you have to perturb this Lagrangian at second order. In perturbation, you can express it like this, with a 0, 0, 0 I component of the metric, or after the SVT decomposition. But in both cases, you can see that it is all of these terms are quadratic in perturbations. You have at most 2 derivatives in each term, and you have these guys here, which are derivatives of the original Lagrangian, calculated at it's a Taylor expansion, nothing more than a Taylor expansion, so it's calculated at the background. So these functions here will be time-dependent functions and are, in principle, are our free functions of time, like the 5 functions of time we have in Ordensky. Here we have some more function of time. So this is not the end of the story, clearly, because in general this will not be gauge invariant. And indeed, we have many terms like this. We have order 100 terms, and this is why I told you that you cannot do it by hand, or you can do it, but it will cost a bit. As I told you, this action in general will not be diff invariant. So what you want to do now is you gauge transform each variable of your action, where psi alpha is my infinitesimal coordinate transformation, and I decomposed it into a time part plus another scalar, di epsilon, plus a vector. And you gauge transform all of these perturbations. Now, clearly, if you want a gauge invariance, you have so now after this operation, you get some L hat, and this will in general not be equal to L2 here, because it's not gauge invariant. So imposing invariance means imposing the equivalence of the two linearized Lagrangian. In order to impose invariance of the Lagrangian, what you have to do is basically you have to calculate to vary the at Lagrangian with respect to the gauge fields, pi, epsilon, and gamma e. This will give you three equations, linear imperturbations, with some k dependence, clearly, some space dependence. All these equations should be equal to 0 and should be satisfied at each, for each k and for whatever choice of perturbation you have. So this will give you a list of conditions on these functions. They can tell you just that one of the functions is 0, or that a combination of them is 0, and so on. After you replace, now what you have to do is just you have to replace all these neutral constraints, which will be a lot. In case of Ordensky, if you have 70 terms at the beginning, they will be like 65 conditions. You replace those conditions here in the original Lagrangian, and your Lagrangian will be left with a minimal set of free functions of time. And this free function of time, in the case of scalar tensor theories, will be the 5 functions we have seen at the beginning. For vector tensor theories, will be some more function. Here, this, yeah.
So imagine that you want to do that with cubic order in the action. Would it be feasible? I guess, yeah.
Consider that, so it's clear, I'm doing it with Mathematica, this calculation. Mathematica is not famous to be fast, but still, scalar tensor theories you can do like in 10 minutes. I never tried. I never tried. With some optimization, I think you can do it at cubic order.
Have many more terms, and then also
exactly.
second order case transformations.
Exactly. But it's kind of automatic. I don't know if it is doable, because I never tried. So here in this table, you can see the functions of time you get in scalar tensor theories and vector tensor theories. So in scalar tensor theories, you have the 4 I already mentioned, plus I'm always neglecting the upper rate. In vector tensor theories, you have 8 functions of time. You don't have braiding, which you have in scalar tensor theories. Now you can see the first difficulty to unify everything. So clearly, if I want to unify 2 theories like scalar tensor and vector tensor, we did more cases. We did tensor theories, we did Einstein-Noether theories, but here, just for simplicity, I show you 2 cases which are representative. If you want to unify everything, you should have an action containing all of these pieces here. Clearly, you'll have 9 alphas, and for example, and the full theory will not represent anything at the end, because braiding is not present in vector tensor theories, and for example, the conformal coupling excess, this other alpha, is not present in scalar tensor theories. So your full theory, composed by all the functions of time, will not represent any of the scalar tensor or vector tensor theories. The other point which makes a unification difficult is that looking at the equations and counting the number of fields you have, in scalar tensor theories you have 4 auxiliary fields, which are the fields of the metric, the perturbation of the metrics, and 2 dynamical, which is 1 matter and 1 the extra propagating degree of freedom. In vector tensor theories you have 5 auxiliary plus 2 dynamical. And so it means that you have 1 more. Or you can clearly remove one of the auxiliary fields and substitute back into the action, getting 4 auxiliary fields, two dynamical fields, but you have to pay the price of having non-local operators. So these are the reason why it's difficult to get a unification. But for practical purposes, for practical reasons, it's okay to unify. I mean, you can always think that you can unify mathematically. What's the advantage of unifying this? Just to not, if you have a code, which a Boltzmann code, say, you can put there a list of equations without having duplicates. This is the only advantage I see. But so these are the practical reasons I mentioned here. But the point is just that you pay the price that your full theory doesn't mean anything. But you can do it, and then, for example, here, how to solve the problem of the extra auxiliary field or the non-local operators. You can keep the auxiliary field, and you can see that if all, for example, these alphas of vector tensor are 0, you are in GR, the constraint, the extra auxiliary field goes to 0 because its coefficient goes to 0 in the Lagrangian. And I'm done with my talk. So basically, just to conclude, I showed just an efficient method to calculate IPhT theories given few ingredients. We are giving a phenomenological description of different theories. And it's possible to write a unified action even if it's not the correct one. Thank you very much.
Hi, thanks for the great review. I don't know if it works. Does it work? Okay, anyway, so my question is on the final part. So once you do all the calculation with Mathematica after choosing the gauge, the fields, and so on, you're left with some number of free functions of time. What do you do with them, or what should I do with them if I wanted to test them? Is there any specific recommendation on should I bin them just in time and space, and then I get 0 constraints? Should I? Is there any prior that from the theory that I should consider? Okay,
it's a good question. So, so basically, the point is, if you have in mind a particular theory of this kind, like a scalar-tensor theory or a vector-tensor theory, say Jordansky, quintessence models, KP, Galileans, what you want, all these functions will have a representation, a time dependence fixed. So if you have some favorite theory in mind, I would say try to mimic that behavior for this alphas.
But sorry, but if I have already in mind to test the scalar tensor, why should I start from the IPhT to go to the scalar tensor? I just start from a scalar tensor, right?
That's right.
For me is how do I actually make use of the IPhT to actually test it without going to a particular model? Some general say recommendation which is not too general, otherwise it's useless. Because
no, the point is that you have to parameterize these functions, right? So either you look at the theory or you look at observations. You can bin them, as you suggested. I don't know how large would be the error bars. What I was suggesting before, it's clear that if you have one favorite theory in mind, you are going with that theory instead of parameterizing the functions. That's true. But what you can do is to explore the parameter space of some theories and maybe realize that one of these functions has always the same behavior, always the same features, and so. This is one way. The other way is going with bin data or nothing, or choose a simple parameterization starting from constant to proportional to the scale factor, and try different things. I don't think I can give you a definite answer, because otherwise I would parameterize my functions myself.
Okay, thanks.
So can I comment on something?
But maybe I don't think that. So now that you have codes like high class or IPhT-CAM, I don't think that anybody that is starting to working on a covariant theory will rewrite these codes again, and we'll just compute the alphas and we'll use the codes that are on the market. So there is no. Well, you just have your model, your favorite model, and you compute the alphas in your favorite model in one afternoon instead of remodifying the CAMB or high class in a month. It's more or less. And yeah. This is one thing, and the other thing. So I mean, there has been a simple parameterization like alpha is proportional to omega dark energy, and there is a study by John Glaze who showed that complicated more this parameterization doesn't really give you. I mean, it's difficult to constrain more complicated parameterization, and maybe with the data, this a simple parameterization will be what the best we can do, basically. So I don't know.
Yeah, I was wondering if there was any study in the first direction that we said. So in trying to understand if there's some common feature, something that is more, say, recommended to use.
No.
Otherwise, I agree that from a practical point of view, for the single model, if you don't have a code already, because otherwise it's useless, it can be more practical to just.
But if you don't have a particular theory in mind, they are all independent of each other. So you don't have any hint on how to relate each other, the function and so on. But okay.
It's just a small question because there is a confusion in the literature. When you're saying a single scalar degree of freedom, do you mean a single propagator scalar degree of freedom? For example, the beyond Hordensky theories and the beyond Procard theories are included in this formalism?
So, for example, yes, no, yeah, in principle, yes, but since I'm requiring at most two derivatives by construction, I'm not getting something that has more than two derivatives in the action. Even if they are spatial and not time derivatives.